All right, seeing that it is 12 p.m., let's go ahead and get started. Thank you so much for sharing your lunch hour with us. Welcome to the third of 4 webinars on how to use sea-level data in the classroom. My name is Abby Wakely, Socorro's Communications Director, and I will be facilitating and moderating the webinar. If you have not already, please watch the second webinar. You can find it here on this link on the Socorro webpage. All participants will be in listen-only mode. You are encouraged to type questions for the presenters or technical questions for me in the bottom right-hand chat box. I will respond to them directly or post the questions to our presenters after their presentation if there is time. We're recording this webinar today and we'll be posting the recording on the Socorro website. Webinar 3 is the Sea-Level Sensor Project and available data from sensors. We are excited to welcome back Jema Sobel and Dr. Alex Roble from the Georgia Institute of Technology. Let's go ahead and get started. Jema and Alex, I am going to promote you to presenters so you can share your screen.
Can everyone see that?
Yes, it's perfect. Thank you.
Great. I don't think we have our video today for some reason, but I think we'll just go ahead regardless, and Jema will start.
Great. Hi, everyone. So on today's agenda, we're going to talk about the Smart Sea-Level Sensors Project. We're going to discuss the science of tides, and the activity that we're going to discuss is an activity about using Fort Pulaski historical tidal data. So the curriculum that we've been presenting was developed in support of the Smart Sea-Level Sensor Project. In May 2018, a consortium of scientists, engineers, government officials, and community organizations came together in Chatham County to form this project, which had been motivated by recent brushes with Hurricanes Matthew and Irma. Schools and businesses were closed for several days after those events created storm surges of over 7 feet and a complex pattern of flooding over a distance of several miles. The project has since expanded to incorporate all of the partners that you see on this slide, with the goal of aiding scientists, engineers, and regional planners in quantifying the short and long-term risks associated with continued sea level rise. The project has installed more than 30 water level and air temperature sensors across the county, working in close partnership with officials from Chatham Emergency Management Agency and the City of Savannah. Over a dozen scientists and engineers are leveraging the sensors and associated data streams for a wide range of research projects, including improved forecasts of coastal flood events and strategies to protect critical infrastructure during flood events. The sensors use the round-trip travel time of ultrasonic waves to measure the distance from the sensor to the water level. They log measurements every 10 minutes, and the sensor data currently includes water level, air temperature, and barometric pressure. So here's some sample data from the sea level sensor that was installed at Fort Pulaski, showing water level measurements, air temperature, and barometric pressure. Depending on how in-depth you would like students to explore the data, you can download the larger CSV file and import it into Excel, or you can simply have students looking at the trends and patterns over the last day or week on the website. At this time, we haven't developed any curriculum that relies on the sea level sensor data exclusively because of its short history, but it can be very handy for comparing local effects to what is being reported at the tidal gauge at Fort Pulaski. So the data is available through the sensor dashboard and provides users with an excellent opportunity to analyze real-time data, especially during times of extreme events. More information about the Smart Sea-Level Sensor Project and available data can be found at these websites and from the webinar that was hosted by Socorro earlier in the year.
Okay, so once you start looking at this raw sea level data from the sea level sensors or a conventional tide gauge like the Fort Pulaski tide gauge that we talked about a bit in the last webinar, what you'll notice, and what you probably noticed on the last few slides, that at any tidal gauge, perhaps as you might have gathered from the name, the largest signal that you're going to see by far is typically going to be the daily tides. And so in service to this, the curriculum includes sort of scientific overview of what causes the tides and what causes deviations from sort of the typical tidal range. So the basic idea behind why we have tides on the Earth is close to the moon, and the moon always exerts a gravitational force on the moon, which creates what's called a tidal bulge of the water on the surface of the Earth. So what that looks like, you can see here in this little animation here on this slide, which you can also go download from NOAA website if you want to use it in classroom activities. What you see here is you see a bulge that is close to the moon, which is simply due to the moon's gravity attracting the water directly from the surface of the Earth, and this causes the water to preferentially get deeper on the side of the Earth closest to the moon. But in addition to that, there's actually also a tidal bulge on the opposite side of the Earth from the moon, and this is because the moon also exerts a gravitational force on the solid Earth. And so what this does is it actually squashes the Earth slightly in the direction of the moon, which sort of a deeper ocean on the other side of the Earth from the moon. And so the result of this is that as the Earth sort of rotates under this tidal bulge with respect to the moon's cycle, what you will see at most locations is 2 daily tides. And so that's, for example, what you see at many of these tide gauges on the Georgia coast. But that's not the case everywhere, and that's because in order for this tidal bulge to exist, water has to be able to flow freely. And so in certain places on Earth where there's sort of a relatively closed bay or other sort of constraint provided by land, there might be only once a day tides. Now, tides aren't exactly the same over time. So approximately once every 2 weeks, or actually once a month, the Earth, the moon, and the sun all align together, which means that the gravitational attraction of the moon on the Earth and the sun on the Earth are aligned in the same direction. So what this creates is basically a period of extreme high tide on the parts of the Earth that are directly in line with the sun and the moon, and then an extremely low tide at the sort of opposite locations on the Earth, or the sort of perpendicular locations on the Earth. And so this tide, which occurs about once every 2 to 4 weeks, is called the spring tide, and that is that extreme high tide is called the spring tide. And the extreme low tide that you'll see at those perpendicular locations is called the neap tide. And each of those will occur once a month. Now, about once every year, this spring tide alignment of the moon, the Earth, and the sun will also coincide with what's called the perigee of the moon's orbit. So the moon's orbit, as you can see in this little schematic here, the moon's orbit is itself an ellipse. So there is a time every month during the lunar cycle when the moon is the closest to the Earth, which means that the gravitational attraction of the moon on the Earth is also at a maximum during that time. When that period, or when that perigee of the moon's orbit coincides with the alignment of the sun, the moon, and the Earth, then there is what is called a perigean spring tide, or what is colloquially called a king tide. So actually, this is typically the time of year, at least here in the southeastern US, this is the time of year when we tend to have king tides, And these are basically the most extreme high tides that you will have in any given year. And so the result of this is that these king tides can lead to flooding because these spring tides can be 1 to 2 feet in some places above the normal tide. So this example, which we talked about in the last webinar of Highway 80, which connects Savannah and Tybee Island in coastal Georgia, Highway 80 flooded in October of 2015 during a king tide event. So there wasn't any significant storm, there wasn't really a hurricane or anything like that. But there was just this king tide, which is something that we expect to happen on a yearly basis, typically around the same time. It's very predictable. And this king tide will often be sort of the first example of what's called sunny day flooding, which is flooding that occurs even in the absence of a storm. And even though sea level rise is occurring sort of in the background to all this very slowly over time, king tides are often sort of the first sign that a particular road or region or neighborhood is vulnerable to sea level rise, because the king tides will be the highest water levels that region will see all year long. On top of that, you can have sort of what we might more typically think of as a storm surge, although it actually doesn't have to be in confluence with a storm. And this is basically when some sort of storm or even just some sort of anomalous atmospheric event causes high atmospheric pressure or high winds going from the ocean towards the coast, and this piles up seawater against the coast and causes sea level to be higher than normal. And so this is the reason why there is storm surge when, for example, a hurricane makes landfall or passes by a region. But also if you just have an anomalously high sea breeze on a particular day or a particular week, this can also cause these sorts of storm or pressure surges as well. Sometimes this also coincides with a spring or a king tide, and the combination of them can potentially lead to quite dangerous conditions. And that's because people don't prepare for these in the same way that you might for a hurricane, where you often have a few days advance notice. So many of the most damaging coastal flooding events that we've seen in the southeastern United States in the past decade or so have been due to these sorts of anomalous pressure surges in coincidence with either a spring or a king tide. So here's just an example again. So we're looking at the Fort Pulaski Smart Sea Level Sensor station. So this is actually a station that was installed right next to the legacy NOAA tidal gauge at Fort Pulaski in coastal Georgia. And so the original Fort Pulaski tidal gauge is the only long-running tidal gauge in coastal Georgia, but this smart sea level sensor gauge was installed right next to it to provide what is basically a benchmark against which to compare the old gauge. And so what you see here is a period of about a week, just from last month, or the end of August and the beginning of September. And I picked this period because it's actually a really good example of what you might expect due to king tides. So the king tide in this location occurred on August 31st. And so if you look at this curve on August 31st, you notice that there's this sort of blip at the high tide that is due to this king tide event. And it corresponds to 1 to 2 feet of water level above sort of the normal high tide water level. And so first there was this event, and then about 5 days later, Hurricane Dorian passed by this location. Didn't make landfall here, but passed by on September 4th. And the interesting thing is that even though you can sort of see the noisiness that comes about due to Hurricane Dorian causing a lot of wave activity in this region. Because the closest pass of Hurricane Dorian occurred during low tide, you don't actually see very much of a signal. So the reason why I'm showing this period is really just that it's a great example of the fact that king tides will regularly occur every single year. They're very predictable, and they will often create flooding events because they're always going to happen every single year, whereas hurricanes, which can produce fairly significant storm surges, if they don't arrive or make landfall at exactly the right time, especially if the storm surge associated with them is only a few feet, they might not necessarily produce the same sort of flooding that you would see with a hurricane that either arrives at high tide or a hurricane with just a very, very large storm surge. All right, I'm going to pass things back over to Jema to finish up.
Okay, so looking at the curriculum arc, we've previously discussed activities that fall within the engage and explore stages, and today we'll discuss the tides activity, which is part of the explain stage. During this stage, students are attempting to explain what they've been learning and exploring. This is really the part in the curriculum where they start to really learn the content included in the module. And you'll see this with the tides activity that we're about to review, and it's also evident in the hands-on activity about sea level rise that we discussed in webinar number 1. So the tides activity picks up where the flooding of Highway 80 activity left off, and it's also aligned with state and national standards. And the activity also highlights the NGSS Science and Engineering Practices, number 4, analyzing and interpreting data, and number 5, using mathematics and computational thinking. As students progress through school, they're expected to explore the use of computers for data analysis, and this activity gives them the opportunity to use spreadsheet software for analyzing a larger data set. All of the title information from Fort Pulaski that they're going to receive for a given month will include over 100 data points. So for teachers, it's probably a lot easier for students to use spreadsheet software rather than spend a week watching them try to hand graph the data. So during this activity, students continue to analyze Fort Pulaski title data from the same exact month that they had previously analyzed in the flooding of Highway 80 activity. Same as before, initially students have raw data which has little meaning to them. And the data set this time also includes the date and time of the recording, the water level, and what tide it was. Previously, they just looked at high tide. Now they're looking at the full data set. I'm sharing screenshots of the data tables just so you can see what students will be looking at, not because we expect you to be able to read the numbers on the webinar. But with all of this data, students need to create a line graph of it, either by using spreadsheet software to graph the entire data set or by hand to graph a smaller subset of the data. So for our purposes today, I've graphed a subset of the data so that you can spot the significant high tides during this month of October 2016, and I've also labeled the high tides that occurred this month. If you remember from the last webinar, any tides of 9.6 feet or higher would result in closing Highway 80. So on 3 separate occasions this month, the highway would have been closed. Graphing the data allows students to visualize the predictable patterns of the ocean tides. It's also setting the stage for students to learn about the role that gravity plays in causing the patterns of these tides. In addition to the tidal data that they've graphed, students receive supplemental information as well, including both a lunar calendar for the month and any relevant weather reports if there happen to be extreme weather events that occurred that month. After they locate the highest tides of the month, they cross-reference those dates with the supplemental information. This extra information, which I've included on the graph, then helps students with their data analysis and to make connections about what is affecting those high tides. Students, and you can see in this case that 12.4 foot high tide occurred when Hurricane Matthew was passing by, and then later in the month you see full moon that occurred at both times of the 9.6-foot high tides. Then students have some reflection questions to answer. And the first couple of questions are designed to help students uncover the nuts and bolts about the tides. How many there are each day, how often they are occurring, when the highest tides were, and if there was any correlation with the lunar calendar. You can give students this information up front, but it's more impactful for students to discover it on their own as they're unpacking the data that they've grabbed. And as students make connections about what influences the high tides, they then take a look at some data visualizations from NASA, tracking sea level changes both globally as measured from the satellites and more locally as measured from coastal tidal gauges, and are asked to consider what impact continued sea level rise might have on high tides overall. If you are implementing the entire curriculum module that we wrote, after this tides activity, you would actually then do the sea level rise hands-on activity that we discussed in webinar number 1. The idea here is that students have looked at the data visualizations and they start to consider what impact sea level rise would have on the tides overall. And then they're going to investigate, well, what in fact is affecting the sea level rise. After finishing that activity, students then watch a 6-minute video that we've included called Watching the Tides, and they answer some follow-up questions. The video explains more of the content, including how tides work, and takes students on a visit to the oldest continually operating tidal gauge in the Western Hemisphere. As a result of this entire tides activity, students should understand the influence that the sun and moon have on Earth's tides, as well as the impact that atmospheric conditions can have on the tides and what that might mean for coastal flooding. So looking at the next webinar, we're going to discuss more global sea level and temperature data and analysis of it. And the activity that we'll discuss is the impact of increased amounts of carbon dioxide on global temperature and what impact students can have on that. Thank you.
Thank you.
Great. Thank you so much, Emma and Alex. If you guys have any questions, you can type them in the bottom right-hand chat box. All right, I'm not seeing any questions. Give it one more minute. All right, there are no questions. Hey, Alex and Jayla, can you put me on mute? I'm hearing it echo. Thank you so much. Thank you guys for attending the webinar. If you do have questions for Jayla and Alex and you want to ask them directly, you can just email communications@socorro.org and I will get you connected to them. And as Jayla said, please join us for the 4th webinar and our last webinar on October 24th at noon. And we'll be analyzing global sea level and temperature data. Thank you guys so much for attending. And once again, if you have questions for Jayla or Alex, please email communications@socorro.org. Have a great afternoon. Bye-bye.